Hello, Rob here from Helix Technologies. Got another video today on helixconveyor.com. Helixconveyor.com is a Helix DeltaT Online Conveyor Design software where you can design your conveyors, you can determine your belt tensions along the conveyor, calculate your starting and stopping times, determine belt traction at your drives, and it's also useful in equipment selection. So I've logged into my account. I've got a subscription for the purposes of this demo, and I'm in my conveyor list at the moment, and from here I can add a new conveyor, so I'll just go ahead and do that. So you enter your details, company name, category. Now the conveyors are grouped by this category, so if you have a project, you can group all the conveyors in that project in this one category. So for this case, I'll just call it mine site A, and you can enter some more project information, so project upgrade, for example. Enter details, and then you can add your conveyor. So this, before we do that, this minimum and maximum site temperature is used for a temperature correction factor, which is just multiplies the friction factor by this factor here for your project. So this is the SEMA temperature correction factor, KT, and basically anything below 0 degrees Celsius, it'll apply this factor. You can have a look at the help file at any time, and it's useful when you get stuck on the program. So we'll look at this temperature correction factor SEMA. It's in here. So anywhere below 0 degrees Celsius, it applies this factor, correction factor. So enter your minimum maximum site temperatures and press calculate KT, and this is the factor that will be applied to the frictions on each section along the conveyor. So we'll leave this off for now because we don't need it. And then I'll add my conveyor. So it's going to create this conveyor in that category. So if you get stuck, just go to your categories, and then we can open the conveyor from here. I'll just introduce you on these pages quickly. From this page, you can list all your conveyors in this category, and you can open them, or you can just view the project details, so you can just edit them quickly without having to open the whole conveyor. You can save from here. You can save as a new file, so this will just save a copy of the file and append the file name with save as, and you can choose your own company logo. This logo will just appear on the report, so it looks quite nice and professional. So I'll go back, and you can also delete your file. You can download the T6 XML file, and you can open it in Helix Delta T6, the desktop version of the program. You can download the JSON file, and you can open it up. You can re-upload it onto helixconveyor.com at any time if you have a subscription. And you can also select multiple conveyor files if you have them in the category, and create a summary CSV file, which is good for doing a side-by-side comparison. And you can save that as a Excel file, and you've got all your data in there. It's quite useful. I'll just copy this conveyor a couple of times just to show you how they appear in this category and how they're grouped. So I've got mine site A selected here. I've just made a copy of this one, so now I can open them both in two different tabs. I'm just middle clicking with my mouse wheel here, and I've opened both of these conveyors in two different tabs. And what I can do is I can change the belt on one of them, for example, and calculate, and then save that one, and then I've got two different versions of the same conveyor. So I can have multiple conveyors and multiple scenarios, and I don't have to change one, calculate, and then reload that same one. And it's pretty useful being able to just chop and change between your tabs and having the different models. I'll just close these and go back to this. I'll delete this one because we don't need it at the moment. And what I'll do now is I'll just talk about the databases quickly. So throughout the conveyor model, we've got equipment inputs, and what you can do is you can select from these databases. I'll just open the belts database. And now these belts are owned by us, but what you can do is you can copy one of these belts, and then that'll be only accessible to you. It'll come up with a username, and you can quickly just filter your equipment by just typing in your email. It's probably the quickest, easiest, but I suggest you create, you can copy it and then you view it or edit it, and then just change the category names. So you can call them my belts, or mine site A belts, just to quickly and easily identify them. So I'll save that one, and then I can open it up, my belts Bridgestone steel, and only I can see this belt. And what I can do is in all my conveyors, I can open the database and choose this category, and I can manually or auto select from that category. You can search text in using the search field. So if I want to search all the S2 2000 belts, the Bridgestone steel ST 2000s, I can just type it in there and they'll come up here. Other databases we've got brakes, fluid couplings, gearboxes, motors, and we've also got a starters database. So now this is used for the dynamic analysis. This includes starters and speed time ramps for stopping as well. So I'll just open up a triple VF drive, a linear ramp category here. So we got 10 second, 20 second, 30 second linear ramps, and I'll open this one. If I scroll down, I can draw the graph here. So this is our ramp. I'll just unselect the smooth curve so you can see that graph. I'll left click. If I press allow zooming graph, I can left click and zoom in on an area, and then just right click to reset. I'll just re-click those, and this is not my data file, so I can't save this one, but if I copied it, I could save it. I can also apply these adjustment factors. So if I want to double the starting time, I can just multiply it by this factor of 2, click adjust, and then now it's a 60-second start ramp. And you can also apply a factor to the torque and the speed of the curve. So feel free to check out all the databases, and I'll just go back to my conveyor list. I'm going to open this conveyor file up, let it load. Okay, so once it's loaded, we can see this is our main drawing. We'll call this the main drawing page, and it's got our profile sketch on it, and our below our profile sketch and our scale drawing sketches, we've got our data tables, we'll call them. Now this is just a default conveyor that we've created for you, but you can delete all your pulleys and start fresh, and then you can just enter your drive details from scratch. But we've just created to get you going, and straight off the bat you can calculate successfully. You can change a component, you can recalculate, view a report, and see the difference. Or alternatively, you can go to the demo conveyors list, and you can copy one of these conveyors and use that conveyor as a template. You can see we've got about 40 different types of conveyors. Some have concave and vertical curves, and some have good dynamic analysis examples in them with multiple drives, so go and check them out. You can create a copy quite easily. On the right hand side, we've got a design summary. We've got the belt capacity, belt strength, absorb power graphs, and we've also got our reports tab. So once we've calculated the conveyor, we can print these reports. We can print a combined report or individual reports and have a quick look. We've also got our tension graphs, a bar graph of all the tensions along each point along the conveyor. You can zoom in on this graph. You left click and drag, and then let go, and then to reset you left click and drag the other way. And we've got all the tension graphs at different load cases here, so you can select your load case and it'll redraw the graph. You can print or save as, or you can even copy the graph and paste it straight into a Word, which is quite useful. We've also got the line graph equivalent here. This is our settings tab. We've just got a few little settings we can apply here to our reports and saving. If I close this conveyor now, it will prompt me, do I want to leave this page? So it's useful if you haven't saved your conveyor, it'll just prompt you first. Just a quick tip on how to use this drawing. You right click and you can drag and you can move around. You can redraw the profile by pressing the refresh button. If you click on a conveyor component, you just got to find its detection box here. You can left click and move it around. And remember, this is just the drawing, the profile sketch. So the profile sketch is drawn by the screen X, screen Z coordinates, and you can change the screen size. If you've got a large diameter drive pulley, such as this case, you can increase this size just so it looks better on your sketch. Enter value in there, redraw, and it'll follow through in the drawing. If you hover over a point, you can see the X, Z coordinate, and this is the screen X and Z coordinate on this drawing. Other buttons on this toolbar, you can save the conveyor using this button or this button. We'll just save it, give you an example. And you can also open your profile drawing settings tab. Here you can change the width and the height of this drawing pane. So we'll change this to 1000. We've got a pretty big screen here. 1300. Apply. You can apply a scaling factor to this profile drawing. And we've also got the adjustment settings, so you can adjust all the X, Y, Z values by a value. You just input the value here, press adjust coordinates, and this will adjust the actual X, Y, Z value coordinates of the conveyor, or you can just adjust the screen X, Z coordinates. So if I can move the coordinates 20 pixels to the right, I can apply, and minus 20, so on, and your Z is your elevation. You can also adjust your luffing angle by degrees, which is useful for stacker reclaimer conveyors, ship loader conveyors. So you draw a base model of the conveyor, you set its pivot point at the 0, 0 XZ point, and then you adjust its luffing angle by however many degrees you want. So for example, I can move this conveyor 12 degrees up, and then I can adjust the screen coordinates down by 50, and it fits nicely on the screen. So yeah, I'll create a base model of the conveyor and then adjust its luffing angle up, save that as a different conveyor file, and then I'll just adjust its luffing angle down, save that as a conveyor file. So I've got the 3 different scenarios: boom level, boom up, boom down, which will give us the varying tensions along the belt, varying starting times. Along this bar, I can also copy the conveyor profile and paste it directly into a Word document or Excel document. And this button I can also access the bar graphs of the tensions. Okay, so since I've adjusted the luffing angle of this conveyor, I don't want to save this, so I'll just refresh the conveyor. It'll reload it from the server, from the version we created before, and it won't save that change. Okay, so looking at the next scale drawing tab. Now this is a 2D drawing of the conveyor, the actual X, Y, Z coordinates. So X is your horizontal plane, Z is your vertical plane, and Y is your longitudinal plane, plan view, which is used for when you've got horizontal curves. The red lines here is the concave and convex vertical curves, and also if you've got a horizontal curve, it'll have a red line showing here. You can change the scale of these drawings. I like to use the 3D scale 3D drawings. There's 3 to choose from here. So this is your elevation. So if I use my mouse, I can zoom in. My mouse wheel zooms in and out of the conveyor here. I can zoom into a drive quite easily. Right click to drag. If I hover over this point, this take up here, I can left click, and if I move this, it will move the actual X, Z coordinate of the conveyor. You might just have to wait a sec, click somewhere to activate it. So I'll just move that back quick. The red line's drawn in from the vertical curve radii we input here. For longer conveyors, you might want to change the Z scale so you can view the vertical curves a bit easier, but in this case 1 can be applied. Another good tip is when you hover your mouse over these buttons, a tooltip will come up just giving you a hint at what it does. So this will reset the drawing, this will just redraw it. If I make a slight change in one of my coordinates, I can just redraw it and it won't change the view. Let's look at the coordinates table. We've got a menu on the left hand side. We can copy, insert before, insert after the item, or we can add a new pulley to the end of the list. We can paste X, Y, Z coordinates from Excel. So we've got the instructions here, so you can follow the instructions, just paste it in there and it'll add the coordinates on. There's also capability to add the return belt intersection points, so from point 11 and back towards the tail pulley, it'll add these points here, the corresponding points on the return side of the belt. Another option is to delete the pulley item. You can delete all the pulleys and then you can start from scratch, add all the new points. Also there's adjust the X, Y, Z coordinates. This will just open this pop-up that we were having a look at before, and you can renumber all pulley items. So after you've added all your items, you can refine which item by using this drop down box, the P-type drop down box. Enter a description. In the drive link column, I've got number 1. Now this 1 corresponds to this drive in the drives tab. So I've only got 1 drive in this conveyor, but you can add another drive here and then link it back to the pulley. Here's your X, Y, Z coordinates and your contact and departure angles from this, the wrap angles calculated. So this contact angle for the drive is 90 and departure angle is 270, giving it a 180 wrap. And the direction of the belt will rotate clockwise around the pulley. Just before I navigate away from the profile sketch, I'll just show you how quick and easy it is to actually build a conveyor from scratch. So I'll delete all the pulleys, items, and I'll just do a quick sketch of what we just had. So I'll start with the tail, add a tail pulley, add an intersection point, which can be my transition, add a hopper, another intersection point, because I might have different idler spacings between after these points here. I'll add another intersection point, this will be my transition point, and then it'll go into and then my intersection point for my concave vertical curve, and then my second transition point to end the horizontal curve, and then then we can go flat, and then we'll have our head drive. We can even add a snub pulley in there, and then intersection point, bend pulley, take up, bend pulley, and then if I enter my coordinates, I can add my return belt intersection points and just enter a separation distance between the top and the bottom of the belt, and then press add return belt points. But make sure you've entered your X, Y, Z coordinates before you've done that. And then once I've done that, I can use my mouse wheel to zoom in, and then I can just make my finer adjustments and make everything look nice and clean. I can also match the screen Z coordinates for a lot of these points to line them up nicely, and then I'll fix up my contact and departure angles to make this look a bit better. Another thing to note is when I add a drive, it'll automatically appear as drive number and the number of drives I've added. So because I already had one drive in here before I deleted all the points, it's added number 2 and number 3 drive, and then I've got to correspond these pulleys to these drives here, and these have automatically been added. I've just got to make sure my load share on all these drives equals 100. I might have 2 drives and a brake, in which case I'll have 50, 50 and 0. I've just refreshed the conveyor to start fresh, and other symbols we've got. This is your hopper, drive, that's your take up, and then this is a brake only. And you can also delete just press the delete item and click on the item you want to delete, it'll prompt you. And also this is your select item, so you can always just press this when you want to move pulleys around. And remember, if you move them around on this screen, it's just going to change the screen X and Z coordinate and not the real conveyor X, Y, Z coordinate. If you want to move the real conveyor X, Y, Z coordinate, you can go to your elevation scale drawing, move your item, or your plan scale drawing, move your item. So once you've entered your geometry of the conveyor, I recommend you view it in the scale drawing and make sure everything looks correct. And then you can go and enter your pulley dimensions. What you can do is you can enter a minimum pulley diameter, and then once you've entered all your other information for the conveyor and you've calculated it, the program will attempt to automatically select an appropriate pulley and it'll calculate the inertia. Or you can manually select manual input and manually enter all these details, and then you can always recalculate all pulley inertias if you've changed these, and this value will be updated here. The program will calculate this calculated shell thickness value, and this is a guide only, and the calculation is from the MHEA, and the calculation comes from the MHEA Conveyor Design Handbook 1986. You can have a look at that. There's more information on that in the help files in the drawing conveyor input pulley dimensions. The next table we're going to look at is the sections table. So once we've drawn the conveyor, it's going to break the conveyor up into sections. So section 1 is a section of belt from section 1 to section 2, and so on. So you select your section type, carry or return. You can enter section description, and it's got the calculated length and lift of each section. Enter your capacity. The red line will be drawn here for sections that have a capacity entered. You can enter your idler spacings, your skirt length, number of scrapers, and these are all used to calculate the resistance in each section of the conveyor. You can enter a different idler rotating mass for idlers that are different to the idlers that you've selected in your idler tab here. And that's useful, for example, for impact idlers. You might have a higher rotating mass. And remember, if you hover over an item, it'll come up with a hint telling you what to enter. Leave it 0 if you don't want to customize the idler mass. Now these two columns here, we've got the F friction factor calculated, and then we've got a input friction factor. So if we know we've got a section of conveyor that has high frictions, we can manually input that section as a higher friction factor, and we can customize each section. If we leave them 0, it'll calculate the friction factor for that section. So for this example, we'll leave all the sections 0. And what we can do is we can apply a ISO friction adjustment factor. For example, if we've calibrated the conveyor and the conveyor in real life is running at a higher frictions to what the program is telling us, we can apply this factor. So I'll type in 1.2 and I'll calculate ISO. This only works for ISO calculations. It'll come up with a warning letting me know I've applied this factor, and it'll apply this factor to each section along the conveyor. I'll just change this back to 1, calculate, you can see came up with a result we had before. And the tension adjustment column is for manually adding additional tension in that section, mainly used for if we've got maybe an impact bed in a loading zone, or an additional force for a loader or hopper pull-out force. Okay, now looking at the brakes table, here we can see we've got one drive, and this drive has a braking torque of 10 kilonewton meters applied, and now this is the low speed brake torque that's applied on the pulley, and this is the brake torque that the program will use for the calculations, the stopping calculations. So while I'm talking about this braking torque, I'll just go to the drives tab. I'll go to my brakes for this drive. I'll set the drive back to manual selection, so it because it's already selected a brake for us, and I can see here that the torque that's applied on the pulley is 10 kilonewton meters. Okay, so the next table we're going to look at is the vertical curves table, and what you can do is you can draw your conveyor, you can calculate it, and then the program will detect if there's a change in elevation in the sections and detect if it's a concave or convex vertical curve. And then you can enter your vertical curve radii. For this example, we've got a concave curve with a 500 meter radius, and if we go to the scale 3D drawing, we can zoom in and view this concave curve. The curve is drawn from the first section to the second section, and it is applied at the point where we enter the curve radii. So for example, this point here, if we hover our mouse over these points, it'll highlight the section so we can quickly see which curve this radius applies to, and it'll apply that radius at that intersection point. So these concave curves coincide nicely, and so do these convex curves here. And then we can move on to our horizontal curves tab. Similar method, you enter your curve radius, but there's a lot more options for horizontal curves. We can customize here our idler spacings, which link up to the idler spacings on the sections tab here. And we've also got our trough angles. We can customize a trough angle for our horizontal curves. We've also got our banking angle, which is your opposite to camber. You can customize the idler rolls, idler widths themselves. And here we can also enter our center and inner and outer US frictions, and also our load shift factors. All these values can be seen in the horizontal curves tab here, where we can draw each individual belt drift graph. We'll look at this in another video in more depth. The next tab we've got is the tensions tab. Now this is just the output tab of the tensions along each section of the conveyor, and it also shows the frictions. So we've got the tight side tension, the slack side tension, the tension required to rotate the pulley, so to overcome the bearing friction losses and the additional tension required to wrap the belt around the pulley. And we've got the effective tension that the drive pulley inputs into the conveyor, and we've got the section effective tension, which is the effective tension over the section due to the belt and the material moving over the idlers, and the tension required to lift the conveyor. So you can see section in the concave curve, section 5 and 6 has a high effective tension for that section. We've also got the material acceleration, the hopper, the tension at the skirts and scrapers, and then the sag tension. The pulley DIMS 2 table just shows some more pulley data, and there's a few more inputs as well, but they're all optional inputs. And in the pulley material tab, you can enter the allowable pulley shaft stress and deflection and shell stresses for the pulley calculations. So now moving on to the other tabs. Here we've got the project tab. We've already covered that. This is the material tab. So this is the conveyed material of the conveyor. And what we can do is we can open our database. We can filter materials. So I can type in iron ore here, and it'll search for all the iron ore materials in our database. Now this is our database that we manage, but you can also customize a material. So you can create a category. You can call it mine site A gravel. Then we can change the bulk density range, and we can add that material to the database, and only you'll be able to see that material. If we open the database again, we'll see that that material's been saved into the database. The important inputs here are the low bulk density, high bulk density, and the surcharge angle. And these are using the belt capacity and belt load and belt width calculations. There's some optional inputs down the bottom for you to identify the material. Moving on to the belt inputs. So the first tab we're looking at is the belt speed and capacity page. The design capacity is metric tons per hour, and this value must be greater or equal to the capacity that was input in the sections table. So for example, you could have different capacities in this table for each section. You could have, if you have multiple hoppers loading onto the belt, you could have 900 tons per hour on the first section, and then the remaining sections you'll have the full capacity. So I'll just make sure that this value is greater or equal to the maximum value in the sections table. This value is used for the capacity calculations here, but the conveyor calculations, tension calculations, are calculated from these inputted values here on the sections table. You can select your belt width using some standard metric and imperial belt width sizes here. Select your idler trough angles and your material low and high bulk densities. These inputs are linked to the material tab we just entered them on, and so is a material surcharge angle. And on this page, what I can do is I can make a change here, and this belt section diagram will update automatically. So if I'm doing my initial design on the conveyor and I want to determine my actual belt width and belt speed, I can use this as a tool to help. So I'll change this to 2000 tons per hour, and can see straight away the drawing changes, and I can see at 2000 tons per hour what my edge distance is, and my minimum required edge distance, my belt percent full, and I've also got some calculated values down here, such as the flooded belt capacity and the flooded material belt mass, which is calculated off the material high bulk density here. So I'll go ahead and just change a few values and you can see the effect. So if I increase my belt speed, here we can see the effect on the belt cross section, and decrease it, I'll just change this back to 3. If I change my belt width to 1800 millimeters, the drawing may look a bit different now, but if I go and change my idlers on the idler page, I'm on the carrier idler page, I'll just open the database, I'll deselect the filter idlers by belt width, and I will choose a category, wait for it to load up, and then I can just choose a 1800 mil belt width here. I'll just find one and select it, and then I can go back and have a look at the drawing. The drawing looks a bit better now. And this belt cross section capacity diagram, the edge distances and calculations are performed from the low material low bulk density here. So if you want to have a range, you'll change this value here and have a look at the effect it has. So it's quite useful. Also, be sure to check out the help files. I've got a help file open here under equipment inputs, belt input, and I can read up on the inputs here, and I've also got some recommended belt speeds from the seam manual on this page, so be sure to check out the help files. Enter your belt top cover, bottom cover, and you can input your belt mass input as well. If you leave this value to 0, it'll automatically calculate the belt mass depending on the carcass mass and the cover relative density. That's found in the belt details tab. Now you can enter your allowable sag percent. So this is the allowable belt sag percent between idlers, and it's used for the take-up tension requirement. When the take-up calculation is on automatic, it'll start at a 500 kilogram take-up mass. It'll do the conveyor calculations. If the belt sag between the idlers is greater than 2%, it'll increment that belt mass another 500 kilograms and then recalculate until the belt sag condition is satisfied. So the sag between the idlers is less than 2%, and also until the drive traction calculation conditions are met. Next thing you can enter is your allowable start tension rise. So this is used for your starting, stopping tensions. Default is 150%, but you can customize that. Some more vertical curve calculation inputs here. Enter your allowable edge tension rise for the convex vertical curve calculations. Your percent belt mass for liftoff calculations. So you want to calculate the worst case scenario for belt liftoff. So it's going to multiply the belt mass by 0.75, and then your concave curve safety factor. The next tab is belt details. So this is the specific details of the belt, and again it's got the equipment database that you can open, and you can select a belt from our database. You can also enter your details of your custom belt and add that belt to your database. Just change the belt category and save that so you can easily identify it for next time. You can also open up the belts in this database view. So if you go data, select the equipment, go to that. I've just opened that in a new tab using the mouse wheel click button, and here I can see in this category I've got all these belts. There's a few different categories you can select from. You can copy any of these belts and change setting, change category, and then you own that conveyor belt, so to speak. You can add new ones from this form as well. You can add a new one and then you can copy it 10 times. You can change a few inputs on each one, and then you've quickly and easily got a few items of your own equipment that you may want to come back and use at a later date. And items in the database that we need to look at. So this is a 4-ply fabric belt strength 1000 kilonewtons per meter. You've also got some optional belt details here, into your minimum pulley diameters for your type A, B, C pulleys, which is used in the belt selection, and your other optional details. The Visco inputs tab is for the viscoelastic calculation method that we have. This is a pretty advanced topic. There's a whole help section dedicated to it, so I suggest you read through this and get familiar with the theory and the inputs, and make sure you have the data, enter the data, and then you can calculate using that. We've got some default values that we've input, which are typical for a low resistance rubber that we use that's a good starting point to compare. And just remember, the viscoelastic method is commonly used in long overland conveyors, especially in high temperatures. Moving on to the idlers tab. Let's look at the idler tab now, and we've got the carry idler and the return idler tabs. Enter your belt width. We've already selected that as 1200 millimeters on the belt page. Enter your nominal idler spacing. So this is 1 meter between idlers. You select your dynamic load factor CA value. You press this button and it'll come up with a lookup table. So this is a dynamic force due to lumps and material impacting on the idlers. The default value is 0.014. Enter a idler vertical misalignment value, and this is a belt deviation load calculator. Now this is an optional input here. The default we recommend is 500 newtons, and this takes into consideration additional loads exerted on the carry side idlers. For example, in a convex vertical curve, there'll be an additional load on the idler, and it's used in the bearing life calculations when we do the conveyor calculations. If the conveyor doesn't have a convex curve, you can set this to 0, although we recommend that you allow for this additional load, as there can be additional loads due to idler misalignment or other installation factors. And scrolling down, this is where we actually select the carry idler for our conveyor. You can use the database again to manually select the idler. Open your database and select your category. We've got a few of our own categories, and again you can add your own. There's no auto selection for idlers at the moment. So enter your idler details. We've got different inputs for your center roll diameter and your wing roll diameters, and make sure you've got a correct bearing C rating. You can check with your idler manufacturers to get these values. And another important input is the idler set rotating mass. So this is a rotating mass of all the idlers in this idler set. So just make sure you get that one right. And I always suggest just draw a quick 3D idler and have a look. I'm just left clicking and scrolling. Enter any additional details, and you can always save your idler and conveyor data using this button here. And then repeat this process for the return idlers. It's the same process, and then we can move on to the take-up inputs. The take-up on this conveyor is vertical gravity take-up, and we've selected the auto calculate take-up mass. So you can select this and the program will attempt to select an appropriate take-up mass, or you can manually select your take-up mass. Just enter the mass or the tension, but we'll leave it on auto calc for this demo. So you've got 4 different options for your take-up type. You can fix centers, which is a pre-tensioned pulley set in a fixed position prior to running, and for this calculation the average belt tension will remain the same throughout the conveyor. So when the conveyor is running, the tight side tension will increase, and then there'll be a corresponding drop in tensions on the return side of the belt. So we recommend an increase in the drive factor, which you'll find on the drives page. We recommend a 0.3 increase in the drive factors for when you've selected your fixed tensions conveyor. So we'll just do an example. I'll just select it, fix centers, and I'll go to my drives page. This is my coefficient of frictions, and I've selected auto calc drive factor for here. If I calculate that, or if I calculate the conveyor, I'll go back to drives, it'll add 0.3 to each of the starting and running drive factors. You can read more about these drive factors in the help file on the drive section. And I'll just change this back to vertical gravity. I'll calculate, and the vertical gravity it's a weight suspended vertically below a pulley to create a constant constant tension in the belt. The horizontal gravity is similar, although it's a pulley on rails, and it's connected to a weight via a pulley rope system. The winch is a constant tension winch, but you just have to make sure that it can react fast enough to the belt movement, or the belt stretch and contraction. And I'll just reselect vertical gravity. So input your take-up increment size. So this is the mass, this is in kilograms. So we've got 500 kilogram increments, and the maximum number of calculation increments is 100. I can set this to 200, or I can increase this take-up mass increment size. And when you calculate the conveyor, the program will attempt to select an appropriate take-up mass to satisfy the running full and the running empty belt sag and the drive traction conditions. The allowable belt sag we entered as 2% on the belt inputs page. And it's important when we're doing the conveyor calculations, we check the take-up and drive traction report to ensure there's a sufficient belt take-up mass for the starting and braking conditions, fully loaded and empty. And what we can see here is the calculated belt T2 tension is greater than the minimum required tension, so the take-up mass is sufficient for this case. And if we see a surplus T2 tension that's a negative value, then we'll run into some belt slip issues, or we may run into some belt slip issues. What I'll do is I'll open up a demo file and just show you another example of that report. I'll open demo 02 up. It's a high lift conveyor, and I'll just calculate and open the take up and drive traction report. And here we can see the surplus T2 tension is negative, so we're going to run into some belt slip issues, and the additional take up mass required calculated by the program is 3.8 tons. And if we increase this take-up mass by that value, then this should eliminate this condition. Other inputs on this page, we can enter some take-up travel distances and estimate our thermal expansion and your belt stretch. So I'll just calculate these and calculate total travel. And I've got a diagram for a vertical gravity take-up on the right-hand side here. Now moving on to the drives tab. On the drives page, we can see there's only one drive on this conveyor. Obviously, you can have multiple drives. If you've got a standard subscription, you're limited to the one drive, but professional and dynamic subscriptions, you can have as many drives as you require. So what I'll do for the drive inputs page, I'll just open up a new demo conveyor. So I'll go to the conveyor demos, and I'll pick one with multiple drives. I'll pick this one here. So I'll pick this conveyor demo 16, open that. And we can see straight away this conveyor's got two drives, a head drive, a secondary drive. There's a snub pulley in between them. And then there's our take up and our brake only. If we hover our mouse over the drive, it'll highlight it down here, and we can see this drive is on pulley number 9, and it's drive 1. The secondary drive's drive 2, the brake's drive 3. These numbers correspond to the numbers in this table in our drives tab. So drive 1 was our head drive, our return drive, which was our secondary drive, and then our brake was drive number 3. So as we click on each drive, it's gonna change what drive we refer to in our input tabs here. So now I'm looking at drive 2, and if I change the motor, it'll only change the motor for drive 2. If I go to drive 1, it'll only change the motor for drive 1. Now what I can do here is I can add drives from this menu here. I can add a new drive here, and the load share needs to equal 100%, so I'll change the load share as necessary, and then I can select that drive and I can remove it. It'll give me a prompt, so I'll just remove that drive. And if I remove a drive on this table, I'll click OK, and then I'll go back to my drawing tab. The drive link is still connected to drive 3, so I've removed the drive for the brake, but the drive link is still there. So if I add a new drive in, that link this will be drive 3, and it'll link to this pulley, this drive here. And if I delete an item on this page, then it'll delete that drive link, but it won't delete this drive. So what you can do is you can change what pulley the drives are on by changing this drive link number. I'm just going to refresh this to remove the changes I've just made. Wait for it to load, and I'll go back to my drives tab. So you can select your drive type: ahead, return, tail, trip, intermediate, or brake. A brake obviously has a 0% load share, and you can move this drive up or down. If I select drive 1, move it down, then I'll select it again, move it down again. This will be drive number 3, which corresponds to drive link number 3. So we don't want that. So I'll just refresh the conveyor again. And now looking at the start full and start empty factors. So the start full factor is you enter the peak starting torque for the drive for a full conveyor, and the start empty torque is for the empty conveyor. Now this value determines the motor torque during starting. At 100%, at 106%, it's going to use 106% of the motor full load torque to accelerate the conveyor. So the higher this value, the faster the conveyor is going to start. Potentially the higher the tensions in the belts are going to be, and the lower the starting factor, the opposite's going to occur. And then we'll have a look at the remaining tabs in the conveyor. So looking at the traction tab, so I've selected drive 1. This is a head drive. I've got 2 motors on this pulley, and the wrap angle for this drive is 178 degrees. Lagging thickness is 12 millimeters. And for the pulley condition, I've selected moist and ceramic lagging for the lagging type. And these are used for our drive traction calculations, which you can see on the report, Takeup and drive traction report. And if you go to the help file, you can go to the drive inputs, drive details page, and you can see and you can read more about the drive traction calculations here. And you can also have a look at the table we've got for the coefficient of frictions. So going back to the conveyor, you can either use that auto lookup table or enter your own, and you can also calculate the drive factors running and starting here, or select your own. So I'll just leave these on, and moving on down, we can see just the information we've entered up here: the load share, starting full, start empty, and the drive efficiency. So when we calculate the conveyor, we'll determine the demand power for the conveyor, and then the absorb power will be calculated using that drive efficiency. We've got 2 motors on this pulley, so we've got 2 drives, and it's going to multiply the inertias of each item by 2 to get the total drive inertia. So we can see we've got a large flywheel on this conveyor, and the flywheel inertia is entered here, and these inertias can be entered on each individual page. So I've got a inertia of 30 for my motor, and if I change this value 32, it's going to follow through to this page. But if I change this value on here, it's not gonna follow through onto the individual equipment pages. So you can customize your inertias on here, and you can calculate and just have a look at the effect it has on the conveyor. It's very useful for when you're calculating dynamic analysis. It makes a very large effect on the conveyor. I'll just calculate this again, make sure it's all correct, and I'll move on to the motors tab. Okay, I've got 2 motors on the pulley of manual selection, so this conveyor's already got all the equipment manually selected, and I can always open the database and then select from our databases or the database you've been working on. And if it's on auto select, the program will attempt to select from the category that you've chosen here, depending on some inputs you've made. And I'll just leave that on manual for now. Make sure your motor speed and all your inputs are correct here, and you've got some optional details. I can always add this, I can always make a change on this motor, and I recommend you change the category manually here, and then you can click this add to database, and I'll save this motor to your database, and you can identify it by this category number. Moving on to fluid couplings, we've got it's direct drive, so there's no fluid coupling, but you can enter your fluid coupling details here. Select your gearbox. We've got auto select for this gearbox, and important inputs here are your gearbox ratio and again your inertias. Make sure they're correct. And then the high speed couplings and the low speed couplings. Now there's only one couplings database at the moment, so it's called shaft coupling. So just open the database and you can select your couplings from here. And then we'll have a look at the brakes tab. So for drive 1 and drive 2 there's no brake, and drive 3 it's the brake, so it's on auto selection. We'll just put this on manual for now, and you can also select no brake on drive, and it'll change the inputs to no brake, zero brake torque, zero design torque, but it won't change this torque on pulley, because this value we've input in the brakes table under the profile sketch on the main drawing tab. So this is the low speed braking torque that's been input here, and it's on drive 3, and it's a constant torque brake, and it's this brake is actually on the low speed side of the pulley because there's no drive, so there's no drive, so there's no reducer, so it's on the low speed side. You can also change the high speed side for other drives. And I can input my brake details, so disc diameter, thickness, my disc speed, which in this case will be my pulley speed, and your maximum clamping force, loss of force % per millimeter, and your pad offset. The number of stops per hour will be used to calculate your brake disc temperatures. Your air gap and number of calipers is defaulted to 1, so if you've got 2 calipers you'll double the design torque and the torque on the pulley. So how we've managed this is, if you enter these details you can calculate your selected brake torque, which will use the Sven-Borg method of calculation here from these inputs. It'll use the minimum clamping force, your diameter, thickness, and your friction, loss of force % per millimeter, pad offset, and your air gap to calculate these values here. Then from this you can enter your design torque and then you can apply this design torque to pulley. So if I press that, it's already 70 kilonewton meters. So if I change this to 7,000 newton meters, I can apply that to the pulley. The reducer ratio, and this is calculated through the reducer ratio that you choose here. See, this is brake only, so the reducer ratio is 1. It's pretty straightforward. I'll just change that back and apply that design, that torque to the pulley. Now when I change this, when I press this button, it actually changes the value that's input here. So just be mindful of that. I'll just show you quickly. Change this back to 7,000, apply that, and it will change this value. And then if I change this, correspond back to here. Might just prompt it, just toggle the drive, and it'll change it here. So that's brake selection, and you can select your holdback that's installed. So we've got a holdback on drive 1 and drive 2, and if there is a holdback, make sure you select this checkbox here. Okay, and there's a couple more tabs. We'll cover the horizontal curves in another video. We'll have a look at the data tab now. So this is just output data. So what you can do is you can just copy and paste these tables and paste them straight into an Excel spreadsheet, and it's pretty useful for getting a lot of data quickly. For example, your tensions, you might want your tensions T1, T2, static tensions at each point, at each of your drives, or whatever you require, but it's pretty handy for that. And I'll talk quickly about the calcs tab. So this is the quick calculations, and here you can perform a lot of quick calculations independent of your main conveyor here. So any inputs in here won't change or affect your conveyor. They're just quick calculations. So enter all your information, you can calculate, and then you can view a report straight away. So we've got hopper pull-out force calculations, your feeder load calculations. So you can perform a calculation here. You can get your feeder vertical load and your feeder horizontal resistant forces here. So I might want to do a calculation, and then I'll input this flowing resistance force 89 kilonewtons into my tension adjustment in the sections tab. So for my hopper section 2, I'll input this 89 kilonewtons here, which is a very high resistance force. And then we can also calculate our discharge trajectories, which also takes into consideration your belt sag on the approach of your discharge pulley. And we can have a look at the graph, discharge trajectory graph that draws as we change the inputs here. And again, you can view a report. You can get the X and Y distances at each time step that you input here. You can change your time step by changing the calculation time span and the number of calculation increments. Calculate your transition distances at your head end and tail end transitions, and your pulley inertias, quick pulley inertia calculation. So you can calculate this, take your inertia value and input it into the low speed pulley inertia input value here. And other calculations we have is vertical curve calculations, determine your minimum curve radius for different conditions to satisfy buckling, edge tension, and your belt liftoff, and also pipe conveyor curves. Some pulley calculations here, L10H bearing life calculation. We've got some general calculations here, some conversions, and a motor power calculation, which is useful for when we calibrate a conveyor. We'll take real life data from the conveyor. We'll take the motor amps that are drawn from the motor at a known load, and speed of the conveyor. So we'll know how much power the motor is drawing, change the conveyor belt speed and the capacity to match that real life data, and we can determine how close our absorbed power is from the calculated power from this motor power calculation. And then we can adjust perform a ISO adjustment factor or manually input frictions on each section. So that calculation we use often for calibrating our conveyor model, belt turnover calculation, and also quick little pulley wrap angle trigonometry calculation here. And once we've entered all the details for the conveyor, we can perform our calculations. So we've got 3 calculation methods. We've got the ISO 5048 calculation method, SEMA, and the viscoelastic method. And when I calculate, it'll come up with a calculation success and a little timestamp, so we can just see when we last calculated. And it will also come up with the calculation method that was last used. And if we calculate SEMA, we can see the change in our power and our belt strength utilization here. Again, when we calculate visco, we can see the difference in power demand and belt strength. So I recommend calculate using all 3 different methods and just do a bit of a sanity check on why the methods are different. And once we've calculated, we can view our reports. So I'll just open up that existing conveyor we were working on before, and I'll calculate this one and we'll view the reports for this one. So the design summary report has a few inputs and calculated values here. We can quickly have a look at the belt power for different load conditions, and the effective tension, fully loaded, maximum minimum tensions, and starting and stopping times. Looking at the tension summary report, this is a running starting tension summary. We can see what our startup torque factors we've selected for fully loaded and empty, and also we've got the tension at each point along the conveyor for the different conditions. Now we can see these values in graph form if we open up these tables here, and we can see the starting full has the highest tension condition at the drive, and braking full is the lowest, and these coincide with these values here. There's further details on the individual tension calculation reports. So this is a run fully loaded report, and we can see our T1, T2, pulley torque, drive, TE tension, and our other tension adjustments, and the ISO friction factors that have been calculated. Now if you calculate with the SEMA or visco method, it will also show the friction factors in this column. Starting and stopping report, we've got some input values, and then we've also got our starting and more details on our starting, stopping times, and some stopping distances as well. The drive details report, be sure to have a look at that, because it's got the required ratio and the ratio that you've selected, and you can use this to ensure you've got the correct ratio and the correct belt speed for your conveyor. So these values here are quite close, and it's also got your drive inertias and your other general drive details that you can review. And then lastly, we've got our dynamic analysis tab, which is a more advanced topic, so we'll cover it in another video. But I'll just do a quick dynamic analysis calculation here just to show you how quick and easy it is. So I've got a dynamic analysis subscription, and I've input my details here. I've got a maximum conveyor section length of 400 meters. So looking at the conveyor, it's a 6.2 kilometer conveying distance, and the lengths of some of these sections are quite long here. So this section is 2 kilometers long, this section is 1.7 kilometers long. So if I've got a maximum section length of 400 meters, what it's going to do is it's going to take this 2 kilometer section and break it up into 400 meter lengths, which will increase the accuracy of the dynamic analysis calculation. And we can perform a friction adjustment factor here, and you've got some optional inputs for take up mass if you've got a capstan winch, and enter your calculation runtime. So this is 200-second calculation, your start, stop, reference time, and time step interval. So this calculation, we're going to calculate for 200 seconds. We're going to perform each calculation at each point along the conveyor at every 0.1 seconds. I suggest the first time you calculate, just leave this variable step ODE solver off, and before we calculate, we'll just make sure we've got our starters selected properly. So in the starter tab, again, we can change which drive we're on by clicking the drive here. So the brake, it's a constant torque brake. This is the braking torque that's been applied on the low speed braking torque that's been applied on the pulley. There's no delay time, and we just have to make sure we select torque speed for the brake, or you can apply a speed time curve here, and in that case I'd select speed time and variable speed time control, and then it'll apply that. But for now, it's a constant torque brake. Just make sure there's any starter curve that's selected, or it won't perform the calculations. For the other drives, we've got a speed time graph selected here, and a torque speed slave drive starter selected here. So I'll just calculate this conveyor. It's going to take a few seconds, maybe 10-15 seconds to calculate on my computer because of the time step interval and the calculation runtime we've selected. And the calculations are performed on your computer. They're not performed on the server, they're performed on your computer. So the time it takes to calculate will depend on that. So I'll just start the dynamic analysis. So that's taken about 15-20 seconds to calculate, and I can see this is a velocity 2D graph. So it's plotted the drive, primary drive, secondary drive, and the brake, and also it automatically plots the tail and the take up. So this take up is the speed of the pulley. So it's not the speed of the belt, it's the speed of the vertical take up pulley movement. And the other lines are the speed at the belt at those points at that time. So we can see the belt speed follows that speed time ramp that we selected, and it starts in 150 seconds according to that speed ramp. You can also enter some comments here, and then these will appear in the reports. So I'll select my tension graph. You can see my belt safety factor is 6.15 for this arrangement that we've got here, and the peak tension is at this time at the primary drive. Well, we've also got the pulley torque graphs and the take up travel graph. You can select other points along the conveyor that you're interested in. So if there's a concave curve, you can select the point in the concave curve to determine the belt tensions in that point. That's useful for stopping fully loaded conveyors where you might encounter low tensions and high belt sag in the concave vertical curves. So that's just a quick introduction to the dynamic analysis, and be sure to have a quick look at your velocity and tension 3D graphs, and you can print your reports, which include your starter graphs and your input data, and then the results. Let's just talk about the sharing capability of the program now. So if you've got an account and you've got your own conveyor, you can open this share pop-up here, and what you can do is you can enter someone's email into this box here, and then you can select their permissions. So if you select both of these, the user can open the conveyor and they can edit it in any way they like, and then they can save that conveyor, and they can also copy it. But if you only select can copy, that user can only copy your version of the conveyor file, and then it'll create a copy in their account, and then they'll be able to change the copy as they please. If you want to give the user can view only permissions, just deselect the can copy checkbox, and they'll only be able to view the conveyor, and they won't be allowed to edit or copy the conveyor. And once you've selected the permissions, just click share, and then you're going to have to save this conveyor to save the share details. So go ahead and click save conveyor and share details. You can also change ownership of the conveyor, so this will relinquish your ownership of the conveyor to the person you've selected, and they have to be in this add share user list and with can edit details. So add them onto this list, and then enter their email in here, and then you'll have to click save, and then save the conveyor and the share details as well to apply this. If you don't want to apply this, you can just back out of this page and nothing will save. And when you're sharing conveyors with other users, it'll come up in a different color here, and it'll tell you which user that conveyor belongs to, so you don't make a mistake. And only the user who owns that conveyor will be able to delete the conveyor as well. So you can have a look at the conveyor ownership by just going to the project tab, and the document owner will come up here. So I own this conveyor, and if I share this conveyor with someone else, they can also go to the project tab and find out who owns that document. I hope you've got a bit out of this video demonstration. We've covered quite a lot of the program here. There's still some more advanced topics to cover, which we'll get to. And just remember, you can create an account for free. Just register, and then you can view the demo files for free, but you won't be able to save any of the changes you make on the demo file, and you won't be able to create your own conveyors. You can go to the subscribe tab and select your subscription, or you can contact us for other options if you want to pay by purchase order. Please contact me with any questions and queries you've got in general about conveyors, or specifically the program, and I hope to see you online soon. Thanks.